Alright, so the first thing we're going to talk about this week is diagonalization. So last week we talked about the idea of finding eigenvalues and eigenvectors, and we're going to get a little bit more into the idea behind why it's so useful to obtain these things. So first, let's kind of notice something about a diagonal matrix. So if we have a matrix D, which is going to be diagonal, which only has non-zero values along the diagonal, if we raise D to some power, what's going to happen is this is going to be the same as just taking each of those entries along the diagonal and raising them to that power. You can try this yourself if you'd like with a couple of diagonal matrices, and then we'll just continue to have zeros above and below that main diagonal. So we can't always just get something that's just this flat diagonal with zeros above and below. We sometimes are going to have to find a way to get to a matrix that is diagonal by doing a little bit of extra work, and this is where our eigenvalues and eigenvectors are going to come in. So just a couple of definitions as we're starting off here. Two matrices A and B are going to be similar if there exists an invertible matrix P such that A equals P times B times P inverse. Or, of course, you could have P inverse B or P. If they're invertible, we should be able to do either way. So what's nice about this for us then is this will allow us to talk about matrices that are diagonalizable. So a square matrix n by n, A is diagonalizable if there exists n by n matrices D and P where D is diagonal and P is invertible such that A equals P times D times P inverse. So this is something that we'd very much like to have. We'd like to have A be similar to some diagonal matrix. So we also can check this idea of diagonalization kind of maybe in a little bit easier way. We talked about how, and yet you see my cat knocking the camera over, and there's the cameras go. Yeah, we're going to leave that in there. So if A is equal to some P times D times P inverse, we talked about how we don't always want to have to calculate P inverse. And so one thing we can do in order to make it so that we can more easily verify that this relationship exists is we can multiply by both sides on the right by the matrix P. And then what happens here is if we have P inverse times P, that'll be the identity, and then that'll give us that if we can verify that A times this P matrix equals P times this D matrix, that would help us verify this idea that A is similar to some diagonal matrix. Let's talk about why we'd like to have something that's diagonalizable. So if we've got A equals PDP inverse, if we want to calculate A to the third, that's going to be the same thing as P times D times P inverse to the third. And so if we wanted to expand that, that'll be P times D times P inverse times P times D times P inverse times P times D times D inverse. And something we should notice is every time we have these P inverse and P's butting up right next to each other, they'll turn into the identity matrix. And so with that, they'll disappear, and what we'll be left with is P times D times D times D times D inverse, or just P times D to the third times P inverse. So what's nice about this then is if we know what P is and we know what P inverse is, we can take any matrix being raised to a large power, and if we know what D is, and what happens is instead of having to multiply by all of these matrices over and over again, we only have to multiply by P D to some power, which we just talked about is actually very easy to calculate because you just need to raise the diagonal entries to some exponent, times P inverse. And so this works for any multiple we can come up with. So if we instead wanted to go ahead and calculate A to the, 100th, this is going to be the same as P times D to the 100th power times P inverse. Now, of course, we would need to still figure out what D is, and hopefully those are numbers on the diagonal that we can raise to the 100th power in our calculator. Some of those numbers are very difficult to find. Even if we had something as easy as 2 to the 100th power, we get something in the realm of 1.27 times 10 to the 30th. So again, as long as these are numbers that are, workable, this is something that's very nice for us to have form-wise. So let's start off with an assumption that we know what D and P are. We'll talk about how we get these in a minute, but let's say we know what D and P are. If we wanted to calculate a to the third, one of the things we're going to need is P inverse. So we just said that a to the third equals P times D cubed times P inverse. So we need P inverse still. So how we find P inverse, remember, if we want to find our inverse for our matrix, we're going to start off by augmenting P with the identity matrix, and what we'll start off with is, because P is 2, 1, 0, negative 1, we'll augment the identity of 1, 0, 0, 1, and then we'll go ahead and obtain our reduced row echelon form. So we get 1, 0, 0, 1 on the left, and on the right we should get a half, 0, and negative 1. And so then this, based on our process, is going to be P inverse. So then A cubed, which is just P D cubed P inverse, will be 2, 1, 0, negative 1 times 1, 0, 0, 2 to the third power times 1 half, 0, negative 1. And so we end up getting 2, 1, 0, negative 1 times 1, 0, 0, 8 times 1 half, 0, negative 1. And when we go ahead and continue all of this, we should get, one second, we should be able to, in the end, obtain 1, negative 7, 0, 8 as a matrix. So let's talk about that. We can go ahead and multiply them in our calculators. We can go ahead and do it manually. We also have some calculator tricks to calculate some of these things if it were to help. So 2, 1, 0, negative 1 is one of our matrices. We also are going to have 1, 0, 0, 8 as another matrix. And we know how to find the inverse on a calculator. So we can go ahead and do, this is our quote-unquote P times our diagonal matrix, and note that we did go ahead and put in that matrix to the third power, and we can go with P inverse, and I can confirm our things. We also could go ahead and have taken and left this as 1, 0, 0, 2, and then we could do our P times our diagonal matrix cubed times P inverse, and we get the same thing. And one other thing we could have done at the start of all of this was go ahead and take, well, we don't have A, but if we had A, we could have went ahead and put it in here and then raised it to the third power as well. So we've got a couple of different options for ourselves. We want to be able to pursue this version though, and we'll see some examples as we go of why. I know we already know that if we want to raise it to even a higher power than 3, it'll become very important to be able to have this nice form to work with. So let's go through a theorem then. Our theorem 12.1 says an n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. In fact, A, which equals P, D, P inverse, where D is a diagonal matrix, if and only if the column of P are n linearly independent eigenvectors of A, and the diagonal entries of D are the eigenvalues of A that correspond respectively to those eigenvectors. So that's a kind of very long way of saying that A is diagonalizable if and only if there's enough eigenvectors to form a basis of Rn. If such a basis exists, we're going to call it an eigenvector basis or an eigenbasis. There's kind of a very long proof here on this page and the next page that we're going to skip for now for time's sake. But what this leads us to is our process for going ahead and diagonalizing a matrix. So if we want to go ahead and try to diagonalize a matrix A, what we're going to do is we're going to start by finding the eigenvalues of that matrix. So we'll solve the terms of A minus lambda I equals 0 and figure out what those lambdas are. From there, we want to try to find a spanning set of linearly independent eigenvectors of the matrix. So for each eigenvalue lambda I, we're going to find a basis for the null space of A minus lambda I times the identity matrix. And then we'll go ahead and take the union of all of those bases for the eigenspaces. So in other words, we'll take each of the eigenvalue or vectors we get and put them together. Now, if we've found enough eigenvectors that we have the same dimension as whatever the matrix of A is, then we have something we can diagonalize. And if we don't have enough, then we can't diagonalize the matrix. So, for example, let's say we had E1, E2, and E3. So E1, E2, and E3 are going to be our eigenvectors, and they are going to go ahead and if we have a 3x3 matrix, this is enough to give us something we can use for diagonalization. But if we have something that's bigger than a 3x3 matrix, we won't have enough. Now, P is going to be constructed by taking the eigenvectors that we obtained and putting them in some order. And our matrix D is going to come from having our main diagonal be those corresponding eigenvalues with zeros everywhere else. So we'll talk a little bit as we go on. The order is important here, but it's important in the sense that you have lambda 1 in the same column as its eigenvector, and lambda 2 in the same column as its eigenvector in the other matrix, and lambda 3 in the same column as the eigenvector in the other matrix. If we switch the eigenvalues around, we have to switch the eigenvectors around as well in the same way. And then our last step for diagonalizing a matrix is just double check to make sure we did everything correctly by checking if A equals P times D times P inverse. But as we discussed before, you can also just check if A times P equals P times this diagonal matrix D. And if you get those things, that can be an easy way to check to make sure that this works. If you only care about finding P and D, say a problem only asks you for P and D. All right, so let's go ahead and try to diagonalize a matrix using some information from problems we've seen before. So let's say we wanted to diagonalize this matrix 5, negative 3, 6, negative 4. In an earlier example, we found that M has eigenvalues of 2 and negative 1, and their eigenspaces are a span of 1, 1. That are associated with our eigenvalues. So I usually like to go ahead and get D in order first. And since we have eigenvalues of 2 and negative 1, we'll go ahead and do 2, 0, 0, negative 1. Now our columns of P have to be the eigenvectors associated with each of those. So the first column of P, since I have an eigenvalue of 2 in the first column of D, is going to be 1, 1. And for our second column of P, because the second column of D is associated with the eigenvalue of negative 1, we need to have 1, 2 as the entries there. So now we have our P and our D matrix, and once we've found eigenvalues and eigenvectors, it's not too difficult to verify or to calculate these. But we want to check does m times p equal p times d? So we can go ahead and take 5, -3, 6, -4 times 1, 1, 1, 2, and verify that that's equal to 1, 1, 1, 2 times 2, 0, 0, -1. So if we go ahead and we make this calculation, what we should see is that we've got, for the first entry, 5 times 1 plus -3 times 1, so 5 minus 3 is 2. Next entry should be 5 times 1 minus 3 times 2, so it would be 5 minus 6, which is -1. Our next entry will come from 6 times 1 plus -4 times 1, so 6 minus 4 is 2. And then our last entry will come from 6 times 1 minus 4 times 2, so 6 minus 8 will be -2. Now we just need to double check that that is indeed equal to what's on the other side. So if we go ahead and find this 1, 1 entry, we'll take 1 times 2 plus 1 times 0, so 2 plus 0 is 2. We will, for the next entry, take 1 times 0 plus 1 times -1, so 0 minus 1 is -1. Our next entry will come from 2 times 1 plus 0 times 2, which will be 2 plus 0, which will be 2. And our last entry will come from 1 times 0 plus 2 times -1, so 0 minus 2 will be -2. So indeed, these two do match, and we've kind of just double-checked and verified that our matrix will be P times D times P inverse. All right, so we had an earlier example, another earlier example where we wanted a diagonal, where we had a matrix 2, 0, 0, 0, 3, 1, 0, 0, 3, and we wanted to go ahead and, or we want to try to go ahead and diagonalize this matrix as well. So we found that our eigenvalues from before were 2 and 3 was repeated. So for the eigenspace associated with 2, we said we had the span of 1, 0, 0. And for the eigenspace associated with 3, we said we had the span of 0, 1, 0. Now, because we have a 3 by 3 matrix, we need 3 eigenvectors, but we only have 2. So since M is a 3 by 3 matrix, we need 3 eigenvectors to diagonalize it, but we only have 2. Therefore, we cannot diagonalize this M. All right, so something of note, this scenario where it's possible, we have the potential to be unable to diagonalize, comes from when we have these repeated eigenvalues. But having a repeated eigenvalue, as we'll see in a later example, doesn't necessarily mean we can't diagonalize our matrix. We still need to go ahead and find these eigenspaces to make sure that we can't go ahead and get what we need. So let's go ahead and do another example where we try to go ahead and diagonalize this matrix. We're told one of our eigenvalues is 4, and its basis is -1 to 0, or the span of that. So our first step, if we want to go ahead through the whole process of diagonalization, is to find our eigenvalues. Remember, to find our eigenvalues, we need to take the determinant of our matrix minus lambda times the identity. So we should have the determinant of 4, 0, negative 2, 2, 5, 4, 0, 0, 5, minus lambda 0, 0, 0, lambda 0, 0, 0, lambda. And we want to set it equal to 0. So really taking the determinant of 4 minus lambda 0, negative 2, 2, 5 minus lambda 4, and 0, 0, 5 minus lambda. All right, now this is a 3 by 3 matrix, so we want to go ahead and do a cofactor expansion. And so we want to go ahead and pick a row or a column that we think is going to make a lot of sense to go ahead and do this through. So I'm going to go ahead and do plus, minus, plus, minus, plus, minus, plus, minus, plus. Now in the scanned version of the notes from last year, I went ahead and used the last row. And so if you want to see this in a slightly different context, you can go ahead and look at the scanned notes for diagonalization. You'll see it in a slightly different method. But for extra practice and to see another way of doing it, I'm going to go ahead this time around and use the center column. So what we'll have then for our cofactor expansion is we'll have negative 0 times the determinant of the matrix we get by removing this row and column. But to be honest, we don't care so much about what that is because it's going to be multiplied by 0. So it'll be negative 0 times the determinant of who cares plus, because now we're on plus, 5 minus lambda times the determinant of the matrix we get by removing this row and column. So we should have 4, negative 2, 0, and, 4 minus lambda, negative 2, 0, and 5 minus lambda. So 4 minus lambda, negative 2, 0, 5 minus lambda. And then we need to subtract 0 times the determinant of the matrix we get by removing that row and column. But again, it's going to be multiplied by 0, so we don't really care. And again, this should end up being equal to 0. So if we take this determinant, what we should get is 5 minus lambda times 4 minus lambda times 5 minus lambda minus negative 2 times 0 equals 0. And so we should get 5 minus lambda, 4 minus lambda, and 5 minus lambda equals 0. And what this tells us then is that we have eigenvalues of 4 and 5, with the 5 being repeated. All right, so as we talked about in the last example, because the 5 is repeated, there's a chance we can't diagonalize this. But we still need to do our due diligence and verify that for sure. So we already said we found the eigenspace for the eigenvalue associated with 4. So basically, remember our process for finding these eigenvalues is to find, or these eigenvectors is to find the null space of A minus lambda times the identity. So when lambda was 4, we found its null space. And what we found is that we had our conditions are x equals negative y over 2 and z equals 0. And that's what helped us bake our constraints in and get this. So if you want to review that, we've got a little footnote down there. Our step then needs to be to go ahead and find the eigenvectors associated with lambda equals 5. So step 2, find the eigenvectors. We know the ones for lambda equals 4, so when lambda equals 5, we're looking at the null space of our matrix A minus 5 times the identity. So that's the null space associated with 4 minus 5, 0, negative 2, 2, 5 minus 5, 4, 0, 0, 5 minus 5. So that's just the null space of the matrix negative 1, 0, negative 2, 2, 0, 4, and 0, 0, 0. So if we go ahead and we put that matrix into our calculator and we get the reduced row echelon form. So we'll do that over on the side here. Negative 1, 0, negative 2, 2, 0, 4. Go ahead and augment a column with zeros on for good measure. Obtaining the reduced row echelon form gives us the following matrix. 1, 0, 2, 0, 0, 0, 0, 0, 0, 0, 0, 0. Lots of zeros. So remember, we should have a free variable for every column that does not have a leading 1. And we want to be careful here. That means that this column, because it doesn't have a leading 1, is going to be a free variable, but this column will also have a free variable. So what this tells us then is y is a free variable, z is a free variable, and x plus 2y equals 0, which tells us that x equals negative 2y. So this is information then we can take to rewrite our null space. So now we have the set of all x, y, z such that x equals negative 2. I don't know why I said y over here. This should be z. People are already probably thinking, man, I was going to comment on that too in the discussion board. So we got x equals negative 2z. We have y and z both being free variables. So we can rewrite this as being negative 2z, y, z, such that y and z are real numbers, and this is then the span of negative 2, 0, 1, and 0, 1, 0. So this is our eigenspace associated with 5. If you double check taking the union of this with our other two eigenvectors, you'll end up seeing that we have a linearly independent set. So I'll save that for you guys to do on your own. And so our next step is to try to form P and D. So we said that our eigenspace for the eigenvalue of 5 is the span of negative 2, 0, 1, and 0, 1, 0. And we were told that the eigenspace associated with 4 was the span of negative 1, 2, 0. So what we can do is we can find our P and our D. Because we have three linearly independent eigenvectors, we can do this by going ahead and making our P be have the columns of eigenvectors and our D be our eigenvalues. So notice that 5 is repeated. So as long as we go ahead and put this in some order that will go ahead and allow us to have our eigenvectors in the same order as our eigenvalues, we'll be fine. So for example, we could go ahead and put 5, 4, 5 along the main diagonal. And then as long as the first column and the last column of P are eigenvectors associated with the eigenvalue of 5, it doesn't matter how we form it. What we're saying here then is that P and D are not going to be unique. There are different ways we can go ahead and arrange these matrices. So for example, we could make the first column 0, 1, 0, because that's one of our eigenvectors associated with 5, and our last column negative 2, 0, 1. And then because our middle column is associated with the eigenvalue of 4, we need to make the middle column negative 1, 2, 0, because it's our eigenvector associated with 4. So this gives us our P and D we would need to go ahead and have in order to diagonalize this matrix. So note that we should also find P inverse, but my guess is after last week you guys are kind of experts on it. So if you guys want a little bit more practice with this, what I recommend doing is finding P inverse and then just multiplying P, D, P inverse together and verifying that you get this A that we had started the previous page with. So make sure you can get this after you found your inverse if you want practice with inverses or just verifying that things work. Now in the next video we're going to go ahead and go through an ice sheet kind of walking through some of the diagonalization stuff, giving you some eigenvalues and eigenvectors for most of these and trying to figure out what different ways we could have, and then also talking about rewriting higher powers of matrices using this diagonalized form. So before you watch that video, give these 4 problems a try on your own, and then when you want to see the solutions, come back and we'll talk about them.